Okay, welcome back to the second half of the talk here. And this, I'm going to concentrate exclusively on working a couple of examples, one from translation surfaces and one from singularity theory, to give you a sense of A, how we actually prove our theorems about monodromy, but also how we end up using our theorem about generating sets for the frame mapping class group. So my goal here is just to illustrate what these generating sets look like and how to actually sort of apply the precise statements that we have. So here's the precise statement of the main theorem, how to generate the frame mapping class group. So we take a frame surface of genus at least 5, and the statement is that it is generated by the Dane twists associated to a particular configuration of curves that we call an assemblage of type E. And these curves, moreover, have to satisfy the condition of being what we call admissible. So what I need to do now is explain what both of these italicized terms are, an assemblage of type E and what an admissible curve is. And having done that, I'll sort of illustrate this theorem in two different applications. So here's the theorem moved up here, and we're going to emphasize first what an admissible curve is. So when you have your framing, it gives you this invariant, this sort of more easy to use structure, which is what we call a winding number function on simple closed curves. And so the idea here, we take our kind of classic running example of a frame surface, and we've got this green curve on the surface. And the thing I want to emphasize is that given this curve or any other curve, you can integrate the change in the angle between the forward pointing tangent vector of the curve and the vector that's specifying the framing. So in this case here, as you compute this, it turns out that the tangent vector winds once around the surface as you move around, where sort of the winding is, of course, measured relative to the horizontal framing vector field. So depending on, I don't remember if it's sort of winding once clockwise or counterclockwise, but in any case, the winding number of this curve is plus or minus 1. So the thing to observe about this is that it's robust under isotopy. That is, the winding number function is a function determined solely by the isotopy class of the framing, and the winding number depends only on the isotopy class of the curve. And so this is kind of our proxy for an isotopy class of framing that we can let the mapping class group act on. So here's another example of a curve on this surface. This one just sort of cuts straight through the surface, and you see that the winding number of this curve is emphatically 0, because everywhere along its path, it's making the same angle with respect to this. And this is our definition of what an admissible curve is. A curve is admissible if the winding number is 0. So these sort of, 0 with a vengeance curves that sort of don't do any twisting at all, those are definitely admissible. There are other more exotic looking admissible curves where counted with sine, which is of course what you're doing when you're computing this winding number, maybe you sort of twist once counterclockwise and then after a while you sort of gradually twist your way back clockwise. That's also admissible. So the statement that I alluded to in the first half of the talk, when does a Dane twist live in your frame mapping class group? It turns out it lives in the mapping class group for non-separating curve, I should say, if and only if it's admissible. And so admissible curves are sort of the only Dane twist that we have to play with at all. So that was relatively easy. Assemblage of type E is a little bit more of an intricate notion. And my whole sort of purpose in this half of the talk is to illustrate what this is and just kind of make it more concrete. So as I said, it's a special set of curves. And it's a sort of, not just a set of curves, it in fact is an ordered set of curves. And the order in which you sort of write this down actually does make a difference. So it consists of sort of two halves, as I've indicated here. There's some set C1 through CK, and then there's some CK plus 1 through CL. And so the core is where the curves C1 through CK live. And we need, this is sort of the genus 5 kind of keeps popping up here, and it's the same 5 in every place. The core has to be a subsurface of genus at least 5. It can have one or more boundary components. I mean, necessarily it needs to have at least one. So the first condition that we require of the curves C1 through CK is that they span the subsurface. And all I mean by this is simply that there's a retraction of S0 back onto this. So kind of, every piece of the surface is accounted for by one of these curves. The second condition that we put on the core is that each pair of curves in the first K curves need to intersect geometrically at most once. Once you have this intersection condition, you can construct the intersection graph where your vertices are the curves C1 through CK, and these are joined by an edge when C1, CI, and CJ actually intersect once as opposed to being disjointed. And so what we require of the core curves is that the intersection graph is a tree. And the final property that we require, and this is the E part of the assemblage of type E, is that we see the Dinkin diagram E6 as a subgraph of this intersection graph. So here's a picture of what a typical core looks like. You have genus at least 5. They're certainly they intersect at most once. This intersection graph you see is a tree, and the Dinkin diagram E6 shows up here. So it's sort of the extra special curve winding around the top, intersecting, and then kind of the 3 middle holes there. So those 6 curves is the E6 Dinkin diagram. So as long as you see this somewhere in the curves in the core, then this is what you need to see. So to build an assemblage, the first thing you need to do is specify the curves in the core, and these are the properties that you need to see for these. So we're not done yet. I haven't told you about the second half of the curve, C1 through CK, or CK plus 1 through CL. And the reason why we insist on ordering the curves here is that the way that we sort of, our mental model for what an assemblage is, and what the terminology reflects, is that we sort of think of this as being a set of instructions for how to build the surface that you're studying by kind of adding on one more curve at each stage. And so the core part is sort of the base case of this induction. And then the remaining curves need to be attached in a good order. So what do we require of this? There's one rule. And the rule is that the next curve that you add on, you look at the surface, a regular neighborhood of the previous curves that you've attached, and it needs to enter your old surface and exit it exactly once. It can't sort of come in and back out and come in and back out. It has to sort of go in, do whatever it wants, come back out. So a thing that sort of is at the heart of what makes this so flexible is there's no intersection number constraints on the individual curves here. It's purely a condition on the subsurface at this point. So here's a sort of typical situation. So here's our core. Obviously, it's not genus 5, but you get the idea. So whatever your core curves are, they're not indicated because they no longer sort of feature in this. It's just a question of subsurfaces. And here's an example of the first curve that I can attach. You can see that now I've sort of added on an extra pair of pants. Each time you add on a new curve, it amounts to attaching a pair of pants. If you enter and exit through the same component, then you're attaching just one leg of your pair of pants. If you're coming in through one component and out through a different component, you're gluing on 2 different legs of the pants. So you're either adding a boundary component or a genus at each stage. And so you see that this red curve that I've drawn in the second surface is a perfectly valid first curve to attach. And then the second curve, you can see I've now sort of had it enter and exit again through the same component. And the thing I'm emphasizing here in these pictures is that the only information you need to track is on the level of the subsurfaces. The intersections with the individual curves are completely irrelevant. So here's just sort of the typical sort of thing that happens. So this is what an assemblage of type E is. It's built by first building the core, where you do have to be fairly careful about how the curves intersect each other. After that, it's a game entirely played on the level of attaching curves to subsurfaces and just checking and see that you run in and out exactly once. So the first example that we're going to look at is in the setting of translation surfaces. And so I'm going to do the monodromy calculation for the stratum H71. This is the stratum in genus 5, where you have 2 zeros of your one form. One has multiplicity 7, and the other one is a simple 0 of multiplicity 1. So to see this, I'm going to start with the topological picture, and then we're going to see that we can realize this topological picture inside the stratum. So the topological picture, I've drawn for you a surface of genus 5 with two boundary components or punctures. I'm going to be a bit sort of floppy on whether I'm treating these as punctures or boundary components. And I'm going to show you how to use our theorem to show that these curves here, there's 11 of them, generate the associated frame mapping class group where all of the red curves are admissible. So in this case here, everything happens in the core. So we're not going to see in this example sort of the second inductive attaching step. So we have 4 properties to check. I'll put them up here, and now let's look at the first one. So we need to see that these C1 through CK sort of span the subsurface. And here this is clear. There's in fact a deformation retraction of the surface onto the union of the curves. So that's precisely what I mean here. The next condition we need to check, inside the core, curves need to intersect 0 or 1 times. That's clear the way I've drawn it. It's also clear that the intersection graph of these is a tree, and the Dinkin diagram E6 needs to appear as a subgraph. In fact, it appears in 2 different places. That's perfectly fine. Here's one copy of E6 that shows up. So we're ready to roll here. And, in fact, we've just checked the 4 properties we need to see. Since the entire surface is the core, our theorem says that these 11 curves generate the associated framed mapping class group. So what our goal is to realize this topological picture as a flat surface living in the stratum H7-1. And so to do this, we need to represent or construct these Dane twists as deformations of flat surfaces. And our basic building block for this is what we call a cylinder shear. So here's another example, a slightly simpler example of a translation surface. And what I've illustrated here, this vertical red curve, and in fact the transverse purple curve, are both the core of what we call a cylinder on a translation surface. And a cylinder is just a flat embedded annulus. And these are really sort of the building blocks of translation surfaces. They're sort of one of the essential features of translation surfaces that you always have to pay attention to. So what's a shear? I'm going to animate it for you. So what you do is you pick, say, the red curve, and you're going to say, I'm going to sort of deform this cylinder that it bounds. And here we go. So what I've done in this stage of the animation is I've simply moved through translation surface land by taking this square and deforming it to a parallelogram. But now, sort of according to the sort of rules for how to identify translation surfaces with each other, you're allowed to cut and remove things as long as you're just doing translations. So what I'm going to do is cut this and move it back down to where it was. And so what we see at this stage is that the shear, where I sort of move one piece past another piece, gives us not just a path, but actually a loop if we shear by the exact right amount. And the thing that you can see in this picture, and this is why I added on the purple transverse curve, is that this is just a flat incarnation of a Dane twist. And that's what I've said here. The monodromy of this loop is the Dane twist about the core. So the upshot of this is that to prove this monodromy statement, we just need to build translation surface with the 11 curves that we know generate the frame mapping class group. We just need to realize them as cylinders. And there's a very nice technique for doing this called the Thurston-Veitch construction. And basically it says if you have a picture like this one, where I've just kind of taken the topological picture, and we'll see how the colors sort of match up with the colors on the flat surface, it gives you sort of a step-by-step instructions for how to turn this topological picture into a flat one. So here's where we see sort of the meaning of the colors. The blue dot on the left side, either a puncture or a boundary component, you can see it incarnated as a 0. And as you sort of count the angle excess, you see that this is a simple 0 of order 1, the blue one. And the red one, you see it shows up a lot more. And if you actually sort of carefully go and count the angle excess, you see that this is a 0 of multiplicity 7. And then the green and the yellow curves on the topological picture, I've just sort of, to anchor yourself, shown you where the green and the yellow show up on the picture here. So this is kind of how you prove these monodromy calculations, is we just sort of build topological models of things that we can prove generate the frame mapping class group. And then we run Thurston-Veach to show that you can get all of these Dane twists as shears. So that's how you prove the monodromy theorem for the setting of translation surfaces. So the second example that I want to show you is an example from singularity theory. And so we're going to be looking at the singularity x cubed plus y to the 10th equals 0. So this is going to be a fairly quick, fairly abbreviated introduction to one of the kind of basic tools for understanding the topology of plane curve singularities, which is called the theory of divides. And so I'm just going to sort of show you what a calculation looks like without really explaining what's going on at each step, because one of my main goals here is to illustrate a more complicated use of the theory of assemblages that generate frame mapping class groups. So our goal is to draw a picture of a Milnor fiber. Now, x cubed plus y to the 10th obviously has a singularity at 0, but if I just take some perturbation of this in the form x cubed plus y to the 10th equals epsilon, and then I look at the set of xy that satisfy this equation in a small ball about 0 and c squared, then I'm going to get a surface which turns out to have one boundary component. And this is going to be what our Milnor fiber looks like. And I need to draw this picture in such a way that Dane twists in my monodromy group are kind of evident on my picture, like they were as cylinder shears in the previous example. So the first step in this construction is to take a careful perturbation of x cubed plus y to the 10th by some lower order terms. That is sort of moved to some clever nearby point in the versal deformation space. And there's a whole theory on how to do this, and it's a really beautiful application of the theory of resolution of singularities. But once we do this and we've sort of done an appropriate perturbation, we graph the solution set. And so sort of up to straightening some things out, if you actually go into Mathematica and sort of write this perturbation down and ask for the solution set in, R2 of this perturbation, you get a thing which looks like this. And now this is what we call the divide for the singularity. And we're going to sort of use this picture to turn it into an actual surface. So the step 2 of this is worked out by Ocampo. We had this real picture, this sort of laced diagram here, which is the real points of a certain perturbation of x cubed plus y to the 10th. And Ocampo then asked the question, well, okay, what do sort of nearby complex points, that is points where the modulus of the imaginary part is very small, what does that look like? And he sort of pushes it back down into R squared. And he shows that it has a very natural structure of a Seifert surface for a naturally associated link. So here's our divide, the real points of this, and there's a recipe for turning this into sort of the complex points. And there's 2 steps to this. The first thing that you do is that you turn each crossing point into a knotted cylinder. So it's a little bit small on this picture here, but if you zoom in on the video, what you'll see is that each one of these sort of things with 4 tabs is actually sort of a cylinder that you build by building in a double twist and then pushing it back down onto the plane. So you replace crossings with double knotted cylinders. Then the second step is you take each of the intervals adjoining these steps and you turn them into bands where you put a half twist in each one. And at this point, you have yourself a surface that is the Seifert surface for this knot or link that is naturally associated to the divide. So this picture we saw in the first half of the talk, and the origin of this picture we now understand as sort of being a picture of the Milnor fiber for the plane curve singularity x cubed plus y to the 10th equals 0. The third step is to draw in the vanishing cycles. And so that's the picture that I've drawn here. So we see there's 3 colors. There's red, blue, and green curves on the surface now. And all of these are sort of distinguished curves that we call vanishing cycles. What a vanishing cycle is it's associated to the singularity. Without sort of diving too deeply into the algebraic geometry, a vanishing cycle happens when sort of a curve is getting pinched off. To hyperbolic geometers, this is a very familiar sort of thing. You have some neck on your surface and it's getting pinched off. This is just some kind of algebraic incarnation of this. We keep track of these curves, and it turns out that these vanishing curves the Dane twists are in the monodromy. This is something called the Picard-Lefschetz formula. So the upshot of this is that not only are these Dane twists in the monodromy, in fact, they even generate the monodromy group itself. So if we want to do a monodromy calculation, these are the things to pay attention to. So what we have to do is we have this collection of curves here, and we need to see that it is an assemblage for, in the sense that I defined previously. And so to take care of this, it actually sort of helps to sort of move away from the surface in this setting and just track things on the intersection graph. And so what I've done here is I've drawn the intersection graph. The color of the vertices corresponds to the color of the curves. And there's intersections exactly when the curves themselves intersect. There's a lot of twisting happening on the surface. And so it's a little bit hard to kind of inspect and see what's happening. But this will sort of tell you the way that the different colored curves intersect each other. So the first thing to look at is, where is the core on this surface? And here we see that obviously there's a lot of intersections between this, and the total intersection graph is definitely not a tree. But these 10 vertices that I've highlighted here do form the core subsurface on your intersection graph here. And you can see that there definitely is an E6 Dinkin diagram appearing inside this. So the remaining thing to see is, if we want to show that this collection of curves generates the associated frame mapping class group, we need to sort of inductively build up the rest of the subsurface. So the question that you have to ask yourself at this point is, can we do this arbitrarily? So, I just picked some random order in which to attach these things. And you have to ask yourself, like, okay, well, if I add on 1, 2, 3, and then 4, and then 5, at each stage, is the resulting attached curve entering and exiting the subsurface exactly once? Now, in this particular example, we don't need to be super fussy about this. We could attach these curves in pretty much any order we want, and we wouldn't run into trouble. So, if you want to be methodical about it, you just attach them from left to right, and you can actually go and verify on the picture that at each stage, the new curve you're attaching is entering and exiting the surface determined by the previous ones exactly once. In general, we do need to be careful with how we order. For more general singularities, you have these same sorts of intersection graphs where you sort of very much don't have the global structure of a tree. So the whole subsurface can't be the core, and you have to take some care to sort of find an appropriate core. And you need to be careful about the order in which you attach things. But one of the things that Pablo and I work out is kind of how to guarantee that this works purely in terms of the intersection graph. And we have this nice graph theoretic criterion to check when attaching the curve associated to the vertex to sort of the current set of curves that we're doing to build our assemblage, when this enters and exits at most once. And using this graph theoretic criterion, what we prove is that the set of curves attached to this divide construction for any plane curve singularity can be given the structure of an assemblage. That is, we sort of tell you how to order the curves so that at each stage, the new curve being attached enters and exits at most once. And so we prove that it's always possible to turn this unordered set of curves into an assemblage. And so that tells you that the associated Dane twists generate the monodromy and leads to our theorem. But I hope that this sort of gives you a flavor of how to use this definition of an assemblage if you find yourself in a situation where you want to do a monodromy calculation of your own and you want to use our theorem. This, I hope, demystifies what an assemblage is and how to sort of work with them. So thank you.